Imagine stepping outside your spacecraft with no helmet on. You take a breath. For about 10 seconds, you feel almost normal. Then your body starts to fail in ways you never expected, not the way movies show it, something stranger. You've probably heard that space will freeze you instantly or make you explode. Almost none of that is true. The real story is quieter, faster, and far more interesting than fiction, and it starts with a question nobody asks enough. What actually happens to a human body the moment air disappears? Let's start with what space really is. It isn't cold in the way a winter morning is cold. Cold requires molecules to steal your heat, and in a vacuum, there's almost nothing there to steal it. Heat can only leave your body through radiation, which is slow, so you wouldn't freeze solid in seconds like people assume. That myth alone tells you how little we intuitively understand about this environment. What else do we get wrong? Here's the first real threat: pressure, not temperature. Your body is built for roughly 14.7 pounds of pressure pushing in on every square inch of you all the time. Remove that pressure and your body doesn't just feel different, it behaves differently at a chemical level. Gases dissolved in your blood and tissues, mostly nitrogen, begin to bubble out of solution. It's the same physics behind a diver's bends, just far more sudden and far more total. Doctors call this ebulism. Your saliva would begin to boil on your tongue not because it's hot but because boiling is about pressure, not just heat. Lower the pressure enough and liquids boil at body temperature. Moisture on your eyes, your tongue, the surface of your skin, all of it starts to vaporize. It sounds horrifying and it is serious, but here's the part most people don't expect. It's survivable for a short window if you get help fast enough. We actually have real-world evidence for this. In 1965, a NASA engineer named Jim LeBlanc was testing a spacesuit inside a vacuum chamber at the Johnson Space Center. His suit's pressure hose disconnected. For about 14 seconds, he was exposed to a near-vacuum environment. He later described the last thing he remembered was the saliva on his tongue starting to boil. He didn't feel pain. He felt himself losing consciousness as the oxygen in his blood stopped reaching his brain. Engineers in the chamber repressurized it within seconds, and he woke up almost immediately with no lasting damage. That single documented case has quietly shaped everything scientists now know about survivable vacuum exposure. So if boiling saliva isn't the biggest danger, what is? Your lungs. And this is where your question gets genuinely fascinating. What if you could breathe in space? What if somehow oxygen was just available out there? Would that fix everything? Not even close, and the reason is almost poetic. The very act of breathing is what would kill you fastest. Here's why. Right now, sitting wherever you are, the air pressure outside your lungs matches the air pressure inside them. That balance is invisible, but it's everything. In a vacuum, that outside pressure vanishes instantly. If you were holding a full breath, the air inside your lungs would expand violently, trying to equalize with the emptiness around you. Your lung tissue can tear. This is called pulmonary barotrauma, and it's one of the most consistent findings across decades of vacuum exposure research on test animals conducted at facilities like Brooks Air Force Base in the 1960s. Researchers studying rapid decompression found something almost counterintuitive. The subjects who survived longest were the ones who exhaled completely and never tried to hold their breath at all. Let that sink in for a second. In space, breathing in could be the single most dangerous thing you do, not the cold, not the lack of oxygen, the act of pulling air into a body that's suddenly surrounded by nothing. So let's actually answer the question properly. What if humans could breathe in space, meaning what if there was breathable air floating around us in the vacuum? Two problems immediately show up, and neither is really about oxygen at all. The first is pressure. Air only works as air, chemically speaking, when it's compressed enough to force oxygen across the thin membranes in your lungs and into your bloodstream. At the pressure of open space, essentially zero, even pure oxygen wouldn't diffuse into your blood properly. You could be surrounded by breathable air and still suffocate because your body needs pressure to actually use it. This is called hypoxic hypoxia in extreme low-pressure environments, and it's a real, documented phenomenon among high-altitude pilots and mountaineers long before anyone thought about space. The second problem is your entire circulatory system. Blood pressure isn't just about oxygen delivery, it's what keeps your blood inside your vessels instead of vaporizing at the surface. Astronauts and physicians like Dr. Jonathan Clark, who spent years studying the physiological risks of spaceflight after the Columbia disaster, have pointed out that pressure loss doesn't just affect breathing. It affects every fluid system in the human body simultaneously. Your body isn't one machine with one weak point. It's dozens of systems that all depend on the same invisible force holding everything together. So even in a world where breathable air magically existed in space, your body would still need something to hold that air and your blood and your tissue fluids at the right pressure. Which means the real answer to your question is strange. You wouldn't just need air in space. You'd need an entire pressurized environment around your body, which is essentially what a spacesuit already is. Isn't that kind of beautiful in a strange way? Engineers didn't invent spacesuits to give you oxygen. They invented them to recreate Earth's pressure in a portable shell wrapped around one fragile human body. The oxygen tank is almost the easy part. Now here's where it gets even more interesting. Let's say we solved pressure completely. Some future technology, some pressurized field, whatever you want to imagine. Could you breathe normally then? Mostly yes for a while, but space brings other threats that have nothing to do with air at all. Radiation is one of the biggest. Without an atmosphere or a magnetic field shielding you, cosmic rays and solar particles would strike your body directly. Long-term studies from NASA's Human Research Program have tracked measurable increases in radiation exposure risk for astronauts even inside spacecraft, let alone fully exposed. Over minutes, this isn't lethal. Over months, it becomes one of the defining challenges of deep space travel. Then there's temperature, but not in the way you'd think. In direct sunlight with nothing between you and a star, your skin could reach dangerously high temperatures on the side facing the light. In shadow, the opposite happens fast. You'd be simultaneously roasting on one side and freezing on the other because there's no atmosphere to mix and even out that heat. It's one of the strangest, least talked about hazards of unprotected space exposure. So why does any of this matter to you, watching this right now on a planet with 14.7 pounds of pressure gently holding your whole body together? Because it reframes something you probably never think about. Every single breath you take right now is doing far more than delivering oxygen. It's part of an enormous, invisible system: pressure, gas exchange, blood chemistry, thermal regulation, all working in perfect, silent coordination every second without you noticing. Evolution didn't build lungs. It built an entire environment-dependent system, and lungs were just one piece of it. Change the environment even slightly and the whole system starts to unravel, not because oxygen disappeared, but because the conditions required to use it disappeared first. This is also why the search for habitable worlds isn't just about finding oxygen out there in the universe. Astrobiologists studying planetary atmospheres, including work published by researchers like Sarah Seeger at MIT, have emphasized that atmospheric pressure and composition matter just as much as the presence of oxygen itself when evaluating whether a planet could support human-like life. A planet could have oxygen and still be completely unbreathable, for the exact same pressure reasons we just walked through. So the next time someone imagines astronauts one day pulling off their helmets in some far-off atmosphere and just breathing freely, remember what you now know. Oxygen alone was never the requirement. It never was the whole story. The real requirement is an entire cascade of invisible physics holding your body together in a very specific, very narrow range of conditions. You've spent your entire life inside that narrow range without ever noticing it. That's not a small thing. That might be one of the most remarkable, overlooked facts about being human at all. And maybe that's the real answer to the question. What if humans could breathe in space? We already do, in a way. Every spacesuit, every sealed capsule, every pressurized cabin is humanity's answer to that exact question. We didn't solve it by finding air out there. We solved it by learning how to carry our own tiny slice of Earth with us, one fragile bubble of pressure at a time. So the next time you take a breath, notice it. Not just the oxygen, the pressure holding it all together silently, perfectly, exactly the way it has to be. Because out there, past the edge of the atmosphere, that quiet miracle disappears in seconds. And you'd learn, faster than almost anything else in your life could teach you, just how much of what feels effortless was never simple at all.